So in this video, we're going to continue our lecture series on thermodynamics, physical chemistry, one at the undergraduate level. So the first thing we want to talk about is in lecture 3, we want to continue by talking about the van der Waals equation. Now the van der Waals equation, a couple things that we need to know about it is that it describes the behavior of real gases. Actually, it describes the behavior of what we call real gases. Since pretty much the ideal gas law fails at high temperatures and low pressures, right? So we have the van der Waals equation that describes the real gases, the behavior of real gases, because with respect to the ideal gas law, it fails, as we said before in lecture 2, and I think we mentioned that in lecture 1 as well. It fails at high pressures and low temperatures, right? The van der Waals equation also represents an analytical approach. So we're going to underline that word analytical because it's important, and we say that the van der Waals equation represents an analytical approach to account for the real gas behavior. So again, the van der Waals equation describes the behavior of real gases, as well as it's an analytical approach to account for real gas behavior. So let's modify the ideal gas law. If we modify the ideal gas law, which pretty much assumes that gas molecules are non-interacting point particles, right? We do this, right? So let's write it out. So which assumes, right? So modifying the ideal gas law, which assumes that gas molecules are non-interacting point masses. We do this by introducing what we call repulsive and attractive terms. Okay? So we modify the ideal gas law by introducing what we call a repulsive term and an attractive term. Repulsive term in physical chemistry is what we define as NB. There's two variables. An attractive term is what we define as A times N squared over V squared, where V is the volume. So let's put that into its proper perspective. So then, to give the van der Waals equation, we say that P, pressure, plus AN squared over V squared times V minus NB, in this case the repulsive term, is equal to nRT. And this, ladies and gentlemen, is your van der Waals equation. So all we did was modify the ideal gas law. Now we need to define the van der Waals equation again. Right? So this is a two-parameter equation, repulsive and attractive term. Right? So it's a two-parameter equation where A, or let me write lowercase a, and B are adjusted for each gas. So depending on the gas, we adjust A or B depending on the gas. Right? So let's look at an example. Let's look at an example how we could use the van der Waals equation. So let's say we have a question that says, okay, what is the volume? So what is the volume? And I'm asking about the volumes of liters of 1.00 grams of nitrogen. 1.00 grams of nitrogen at atmospheric pressures. Right? At atmospheric pressure and room temperature. In this case, room temperature is defined as 25 degrees Celsius according to the van der Waals equation. Right, so this is the question that we have to answer. Right, and I just shortened van der Waals equation as VW equation. Right? So how can we answer this question? The question asks, what is the volume of a 1 gram, essentially 1 gram of nitrogen at atmospheric pressure and room temperature according to the van der Waals equation? Well, we know that the van der Waals equation is equal to P plus AN squared over V squared times V minus NB, which is equal to nRT. So we know that is our van der Waals equation. Now, if we take nRT on the right side of the equation, then we get P plus AN squared over V squared times V minus NB minus now nRT. This equation is equal to 0. Now, if we multiply the expressions out in parentheses, right? So if we multiply the expressions, so if we multiply out the expressions in parentheses, then what we simply get is that PV minus NBP, right? All we're doing is multiplying out, plus AN squared over V minus AB N cubed over V squared minus nRT, and that is equal to 0. So the only thing we did was multiply the expression out. Now, how can we modify this a little bit? If we multiply, so if we multiply through by V squared, so if we multiply the equation above out through by V squared, then PV to the third power minus NB PV squared plus AN squared times V minus AB, so minus AB N cubed minus nRT V squared, this is equal to 0. So that's by multiplying the equation above through by V2. So stay with me. Now, if we collect the terms, then essentially what we have is that PV cubed minus, in parentheses, we're collecting the terms, so NBP plus nRT times V squared. And the only thing I did was, again, I put these in parentheses and factor out the V squared, right? Plus AN squared times V minus ABN to the third power is equal to 0. The last thing I want to do mathematically is divide. Right, so if we divide through by P, then essentially we get V to the third power, V cubed minus N over P times BP plus RT times V squared plus AN squared over P times V minus AB N to the third power over P, and this is equal to 0. So the only thing I did was I took the equation above and divide through by p. Now, by this, we get to what we call a cubic equation. Right? So this, in other words, is a cubic equation. All right? So this is a cubic equation in volume. So there's several different methods for the cubic equation that we just derived. We could use several different methods to calculate. So we can use several different methods So this is where we use several different methods to calculate. In this case, we could use a handheld calculator. We could use a computer, like something like MathCAD or any mathematical software. We could use Newton's method, or we could actually find any analytical roots. So we could solve the equation above by using the methods that we just spoke about. Now, let's say we derive some numbers. So for N2, A is equal to 1.390 atmospheres liters squared mole inverse. And let's say B is equal to, let's write this out here. Let's say B, that is equal to 0.03913 liters mole inverse. All right. And let's say W, which is equal to the weight, that's equal to 1.00 grams, which we know in the problem. And let's say the number of moles, N, for this is equal to 0.03570 moles of N2. Right? So one thing we did was took the grams and calculate it to moles. Right? We already said that T was room temperature, which is in this case 25.00 degrees C, and again in kelvins, that is equal to exactly 298.15 kelvins. R, we know that's the ideal gas constant, and this is equal to 0.08206 liters atmospheres Kelvin inverse mole inverse. Right? So now that we have some numbers, we plug in the volume. So we plug in these numbers. So if we plug in the above values, so plug in the above values, then essentially, if you're right, let's move this up. Then essentially, we get V squared, or I'm sorry, V cubed minus 0. I'm sorry. Let me erase this. So that becomes V cubed minus 0.8748 times V squared in this case, plus 1.771 times 10 to the negative 3 times V minus 2.474 times 10 to the negative 6, and this is equal to 0. So this is the cubic equation that we were talking about. So if we solve for V using the van der Waals equation, we actually find that V in this case is equal to 0.8728 liters exactly. Now, interestingly, so this is using the van der Waals equation. If we actually used the ideal gas law method instead of the van der Waals equation, we will actually find that V is equal to 0.8734 liters. So the ideal gas law, in essence, is a close approximation to something for real gas. Now let's switch and talk about Newton's method of iteration. So this is Newton's method of iteration, or what we call the newton-raphson method. Right? And this is the idea that to find roots of the equation of some equation f of x is equal to 0, we employ the following iterations. Right? So we start with what we call a guess. So Newton's method of iteration says that to find the roots of some equation f of x is equal to 0, we start with what we call a guess. We start with what we call a guess. And this guess is x sub 0. So x sub 0, so if we write it out, x sub 0 is the starting guess. Right, for a root. So for a particular root of the equation f of x is equal to 0, we'll start with a guess x sub 0. Okay. Now, if we use x sub 0, so using x sub 0, we can calculate x1, and that is equal to x sub 0 minus f of x sub 0 divided by f prime of x sub 0. Right? And in other words, x1 is a first approximation to a root. Right? So x1 is the first approximation to the root. Right? We could also use x1. After we find it, we can calculate it. We can calculate what we call x2 essentially. And x2 is equal to x1 now minus f of x1 divided by f prime of x1. Right? And then this becomes x2 is that second approximation to the root. Right? So x2 becomes that second approximation to the root. And you can kind of see the pattern here. Now that we found x2, we could actually use x2 and we could calculate now x3, and that is going to equal to x2 minus f of x minus f of x2 divided by f prime of x2, and that will equal to x3, which is the third approximation to a root. So you can kind of see the pattern, right? So and this goes on and on, etc. So then if we summarize it, we could say that using xn, where n is some arbitrary value, we could calculate xn plus 1, and that is equal to xn minus f of xn divided by f prime of xn. So the only thing I did with this last equation was we summarize the kind of pattern that we see with respect to the iteration. Right? So essentially, we continue until the difference between the successive iteration is negligible. So it's, in other words, let me write this. So we actually continue. So we actually continue until the difference between successive, and I know I spelled that wrong, but we're gonna get over it. Alright, so we continue until the difference between the successive iteration, the iteration is actually negligible. So in other words, that means that we continue pretty much until xn is approximately xn plus 1. Right? Now, let's talk about some of the advantages of Newton's method. Advantages of Newton's method. Right? It's actually fast and simple. We say it's actually good for simple functions such as polynomials. Right? So good for simple functions such as examples would be like polynomials. And then we say it's best if the first guess is actually approximately, well, it's best if first guess is already approximately known, right? So another advantage, which I'm not going to write, is that it's best if the first guess is actually already approximately known, right? So in our case, we have, and this is continuing from the equation above, using the iteration method, we have f of v is equal to v cubed minus 0.8748 v squared plus 1.771 times 10 to the negative 3 times v minus 2.474 times 10 to the negative 6, and that is equal to 0. So this equation that I just wrote is a polynomial, and a first guess to the root is approximately known from the ideal gas law. So this is therefore a good candidate for Newton's method. Right? So again, let me repeat that. This equation above is a polynomial, and the first guess to the root is approximately known from the ideal gas law. So therefore, this is a good candidate for Newton's method. Right? So therefore, if we differentiate, so differentiated f of v, and this goes back to your calculus, f prime of v is equal to 3v squared minus 1.750 times v plus 1.771 times 10 to the negative 3. So that's taking the derivative. Right? Now, from the ideal gas law, we said that V0, the first guess, is already known. Right? So this is equal to 0.8734 liters. And this is the first guess from the ideal gas law. Right? So this is the first guess from ideal gas law, where now V is equal to nRT over P. So that is what V0 is. Now V1 is equal to V0, and this is minus, excuse me, getting ahead of myself, because physical chemistry is so amazing, but V1 is equal to V0 minus F of V0 divided by F prime of V0, and that is equal to approximately 0.8728 liters. And you can see that if we do the same thing, V2 now is equal to V1 minus F of V1 divided by F prime of V1, and this is also equal to 0.8728 liters. So what am I saying? What am I saying here? If that is the case, therefore, since V2 is no different from V1, the method is said to have converged, right? So because V2 method is no different from V1, in other words, I get the same number, we have what we call convergence. So 1 root of f of V1 is equal to 0, is therefore V is equal to 0.8728 liters. So this was accomplished in a mere 2 iterations. Thus, using the van der Waals equation solved by Newton's method, the volume of nitrogen is still 0.8728 liters as obtained before. So that is astronomically really good. Right? So the fact that we used 2 methods, again, V1 and V2 is no different from each other. We said that we spoke about the idea of convergence. And again, this was only accomplished with only 2 iterations, right? We didn't have to go to 3 or 4 or 5, only 2. And thus, using the van der Waals equation again, solved by Newton's method, the volume again is 0.8728 liters as obtained before. For some clarity or for some information, for analytical roots, and you can do this in your own time. We have the handbook of mathematical. We have the handbook of mathematical functions, and that's a handout by Abramowitz and Stegan. So you can find that and do that and look at those roots in your spare time. Now let's switch roots. Let's switch topics to the kinetic theory of gases. Right, so let's talk about the kinetic theory of gases. So to understand the physical basis of the ideal gas law, we actually construct a model, based on the following hypothesis. Right. So there's our hypothesis. So this is the hypothesis. Right. So to really understand the physical basis of the ideal gas law, we construct a model based on the following hypothesis. Number one. Right. Any macroscopic gas. So any microscopic gas sample, it contains a large number of particles, each with mass m, and this is a turbo m, but each with mass m and the diameter d. So m and d are the masses and stands for mass and diameter respectively. The second one is these molecules are actually ceaseless random motions. So they are in ceaseless random motions. So these molecules are in ceaseless. These molecules are in ceaseless random motion. In other words, constantly colliding with each other and with the walls of the container. So, in other words, we say it's a perfect elastic collision. So this is based on our hypothesis. The third part of the hypothesis says that the particles are small. So these particles are small. So in other words, diameter of the particle is way less than the container dimensions, right? So diameter d is way less than the container dimensions, right? Or we could say that the diameter is less than the average distance between the collisions. So this is also another way of saying it, is that the diameter is less than the average distance between collisions. Right? The fourth part of the hypothesis says that no other interaction except for collisions. Right? So in other words, only collisions. Right? So no other interactions except for collisions. The fifth part of the hypothesis says that we're using classical mechanics. So we're using classical mechanics. I'm sorry, mechanics. This is mechanics, but I just wrote it terribly, right? So the fifth part of the hypothesis says that we're using classical mechanics. In other words, Newton's law of motion. Right? So in other words, we want to get an expression for P, the pressure, of such a collection of particles which originates from the constant collision other particles with the container walls, right? So the idea is that we want to get P of such a collection of particles which originates from the constant, obviously, collision of the particles with the container walls. So how can we do that? We have several methods, right? The methods we have is we can calculate a change in momentum when one molecule strikes a wall. So we can calculate the change in momentum Alright, so calculate the change in momentum when one molecule actually strikes a wall. Alright, that's one method we could get to, or pressure. Or we could use a second method by calculating the total number of collisions per unit time per unit area. Right? So we can also calculate the total number of collisions per unit time per unit area. We can also use another method by actually using methods A and B. So using A and B, methods A and B, we can actually calculate what we call the net force. So we can actually calculate the net force per unit area, right? And that is equal to, again, pressure. So those are the three ways that we could go about calculating the pressure. Now let's revisit physics for a little bit. We say that the force exerted by one molecule. So the force exerted by one molecule on a container wall, the force exerted by one molecule on a container wall, we say that the force, and we have our vector, is equal to the mass times the acceleration. And this, again, is what we call Newton's law. So the force is equal to the mass times the acceleration. What I'm really saying, where acceleration, A, the vector over it, is equal to the change in velocity over the change in time. Right? So if that is the case, then plugging in the change in velocity over change in time for our force, we say that now our force, or in other words, let me write it. Yeah. So our force, that is equivalent to, and this just looks terrible, but we want to be consistent. So if that is the case, then we say our force is equivalent to the mass times change in m times v divided by dt. Now, alright, so now m, which is the mass, so m, the mass of each particle, is a constant, right? Is actually what we call a constant, so we can write it as, again, f with our vector is equal to d mv over dt, because m is a constant. Right? Now, this is pretty much equal to the change, is equal to the rate of change of momentum, m times v. Right? So what I wrote here is equal to the rate of change of momentum. MV. So if we look at a box here, and my drawing is terrible, if we look at a box here, and let's say that this is right here, and let's say we're looking at a cubic box, and we have some particle, and let me use a different color. We have some particle, and let's say that this is the negative x direction, and this is the positive x direction. If they look at some arbitrary mass in a box, it may hit this side of the wall, go in the negative direction, and then it may go in the positive direction. So we're looking at some particle which has a mass m. It also has a velocity v, and it also has now momentum m times v. Now this is the length of the cube. Right? Now the reason why we drew this is the idea that we want to illustrate what we call elastic collision, right? Which was within our hypothesis above. So before the collision, the x component. So before the collision, the x component of the momentum. So the x component of the momentum is actually m times negative vx. So before the collision occurs, the x component of the momentum was m times negative vx, right? Or in other words, this is equivalent to negative m vx, again in the x direction. And after the collision, the x component of the momentum is now m times vx in the positive direction. So why do we need to know this? We could therefore say that then the net, right? So the net change in the momentum of the particle we could therefore say that the net change of the momentum of the particle is now mvx in the positive direction minus mvx in the negative direction, and this is essentially equal to 2 mvx. The only thing we did was add in the positive direction and the negative directions. That's the net change, the positive direction minus the negative direction, or v1, or in this case v2 minus v1, or the momentum 1 minus the momentum 2 minus the momentum 1. So the time interval between successive impacts is actually what we call 2L that we mentioned above over Vx. So if that is the change, if that is the time interval between successive impacts, this then now occurs. So the rate of change of the momentum now is 2mx over 2l vx, and that is equal to mvx squared divided by L, which is equal to the force. Now, if we already find the force, we now know from physics that the pressure, which was our initial goal, P is equal to the force over the area. So that's the definition of pressure, which is equal to mvx squared over L divided by L squared, which is the area. And if we divide through, we should get mvx squared divided by L cubed, which should make sense since we were dealing with a cube essentially. Now, for a cube, L to the third power we know is equal to the volume. So L to the third power is equal to the volume of the cube. So therefore, we could then say that P is equal to mvx squared over V. Right? The only thing I did was substitute L cubed for volume. Now, for n molecules, all with different speeds, so this is all with, so for n molecules all with different speeds, we could say that then the pressure now is equal to n times m vx squared divided by v. So this is for any number of molecules. Now we need to define this bracket here. This is where Vx squared is what we call the mean square speed in the x direction. This is an important concept. This is the mean squared speed in the x direction. So we got to do some more mathematical manipulations. V squared is essentially the same thing as V, the velocity dotted into the velocity. And that is equal to Vx squared plus Vy squared plus Vz squared. It's a three-component system. So if that is the case, then therefore the mean square speed, V squared, is equal to brackets Vx squared plus brackets Vy squared plus brackets Vz squared. And that's what we define as for the mean square speed. Now, if we resolve the orthogonal components from the dot product of V dotted into V, which is a dot product, then the velocity component essentially are independent of each other. So again, if we resolve the orthogonal components from the dot product of V dotted into V, the velocity components are independent of each other, so there's no relationship between each other. Now, for a gas, the molecules actually move in a random direction. So for a gas, the molecules move in random directions. So if that is the case, this leads to the conclusion that the mean square speed in the x direction is pretty much equal to the mean square speed in the y direction, which is pretty much equal to the mean square speed in the z direction. So if that is the case, therefore, we can actually write, then therefore the mean square speed, v squared, is equal to 3 times vx squared. And that is essentially equal to 3 times vy squared, which is pretty much equal to 3 times, and let me move this over, and that is pretty much equal to 3 times vz squared. Or, in other words, if we simplify this, we could say that v in the x direction squared, or the mean square speed in the x direction, this is equal to v squared over 3. Now, if we substitute it in the expression obtained above for p, we actually get, so if we do a simple substitution for this, if you go back in the lecture, if we substitute the expression we obtain above for p, we actually now get that p, the pressure, is equal to n for any number of molecules times m, the mass, divided by times the mean square speed. And this is all divided by 3 times the volume. Or we could say that PV is equal to n times m times the mean square speed divided by 3. And ladies and gentlemen, we have just derived the pressure. These two equations are valid. So n, the number of molecules, like we said before, we can actually convert to n, the number of moles, right? So we can easily, in other words, we can easily convert n, which is number of molecules, right? We should convert that to lowercase n, which is the number of moles of the molecules, right? So again, we could convert big capital N, or uppercase N, the number of molecules, to n, the number of moles of the molecules, by using the following relation. So we could do that by using the relation now. N is equal to lowercase n, the number of moles, times Na, right? And the parameters is that lowercase n is equal to the number of moles again. And Na, that is equal to Avogadro's number. So n is a lower number, lowercase n is the number of moles, and uppercase n A is what we call Avogadro's number, right? And we know this from general chemistry to be 6.022 times 10 to the 23rd mole inverse. So if that is the case, this gives us what we call now P times V is equal to N, lowercase n, number of moles, times Na, which is Avogadro's number, M, times the mean square speed divided by 3. Now we actually need the mean square speed. So now we actually need the mean square speed, v squared. Now, how do we get it? we now say that the probability distribution, the probability distribution function f of v. So the probability distribution function f of v gives the probability of a gas molecule having a speed v. Right? So the probability distribution function f of v gives the probability of a gas molecule having speed v. Now let's look at some properties of the probability distribution function. So if we look at some properties of the probability distribution function, what are some of the properties? The first one we want to look at is the idea that if we take the integral from 0 to infinity of f of v, the probability distribution function dv, that is equal to 1. And this is for all possible values of v. The second one that we want to look at is the idea that the fraction of molecules which have speeds between v and v plus dv is given by f of v dv. So let me write this out. The fraction of molecules which have speeds between v and v plus dv is actually given by f of v dv, where dv is pretty much infinitesimally small. So dv again would be infinitesimally small. The third property of the probability distribution function is that the fraction of molecules have speeds between VA and VB, and is defined by, again, the integral from VA to VB f of v dv. So again, the fraction of molecules having speeds between VA and VB is the integral from VA to VB f of v dv. Now, what about the averages? If you look at the averages, we could then say that the average of v, and this is how we write the average in physical chemistry, is equal to the integral from 0 to infinity of v f of v dv. And the average for v2, for v squared, the average for v squared now is equal to the square root from 0 to plus infinity of now v squared times f of v dv. And we could actually really do the same for vq. So then we could say that this probability, so the probability distribution function, and this is on background, was first worked out by Maxwell, or James Clerk Maxwell, and Ludwig Boltzmann. Right, so it was first worked out by Maxwell, or James Clerk Maxwell, and Ludwig Boltzmann. So this is some physical chemistry background for you guys. Now the equation, the probability distribution function, says that now f of v is equal to 4 over the square root of pi times m, which is the mass over 2kb, times t raised to the 3/2 power. And this is times v squared, and epx is what we call an exponent, so everything in the parentheses is raised to the exponent e, negative mv squared divided by 2k bt. This, ladies and gentlemen, is the probability distribution function. Now, some things we need to know about it is that kb is called the Boltzmann constant. kb is called a Boltzmann constant, which is actually equal to r over Na, Avogadro's number, and this is equal to 1.380 times 10 to the negative 23rd joules Kelvin inverse. So kb in that formula is the Boltzmann constant. So what do we need to know? Right? Continuing on the probability distribution function, so we could say that from the properties of a probability function, as we described above, we could then say that v squared, the average of v squared, is equal to the integral from 0 to infinity of v squared times f of v dv, and that is equal to the integral from 0 to infinity of 4 over the square root of pi times m over 2kb, which is Boltzmann constant, times t, the temperature, raised to the 3/2 power, times now v to the 4th power, and we're going to use exponent as e, and everything is raised to the exponent. So this becomes negative mv squared over 2k bt, the Boltzmann constant, times the temperature, and we must put our dv. Now, as you can see, this is an integral, right? So if we continue, we say that from the integral tables, and we're not going to worry about those complicated integrals in physical chemistry, but from the integral tables, especially, we spoke about Abramowitz, and Stegen, so that's S-T-G-U-N. We actually look up those integrals, and from the equation above, we get that the integral from 0 to infinity is now equal to v to the 4th power exponent a negative av squared. And again, these are what we look up from the table from Abramowitz and Stegen. And if we take the integral of this is equal to 3 over 8 times the square root of pi over 8 to the 5th power. So in our case, A is actually equal to m over 2kb times t. So this is what our A is equal to. Right? Again, that's 8 to the 5th power. So if that is the case, we can then say that the average of v squared is equal to 4 over the square root of pi times m over 2kbt raised to the 3/2 power times 3 over 8, the square root of pi divided by m over 2k bt. And this is raised to the 5th power. Right? So you can see that how complicated this gets really quick. So after we cancel out, if we do, I'm not going to do the math here, but essentially after we cancel out all these constants, then the expression actually reduces. So the expression actually reduces to the average of v squared is equal to 3k bt over m, where m is our mass. Now, if kb, which is the Boltzmann's constant, is equal to r over na, like we said before, then we plug it in, we then get that v squared, or the average of v squared, is equal to 3rt over m na. So the only thing I did was plug in the Boltzmann constant for kb. Now, if we plug in this expression for the average of v squared. So plugging into PV is equal to n times NA times m times the average of v squared over 3. So if we plug v squared into PV is equal to that that formula, then essentially we get, right, so all I'm doing is plugging in v squared. So I'm plugging in this whole expression for v squared into this equation. So if that is the case, then we get PV is equal to N, number of mole, times NA times M over 3, and this is all multiplied by 3RT over M NA. And again, this is M, the mass. Now, you could see that if you do a great deal of canceling out, we actually get PV is equal to nRT, which you actually learned in general chemistry. So in other words, the ideal gas law follows a simple consequence of random molecular motions in the gas phase. Or in other words, the pressure exerted by a gas is simply a direct result of random motion of the gas molecules. Again, this all reduces again when we do our canceling out for the equation above. We get PV is equal to nRT. And that is it for lecture 3.